Hello there and welcome to the series of videos going through the content of A-Level Further Maths. Here we're looking at series proof by induction so we can answer questions from exercise 8a. So there's lots of different ways of proving mathematical statements. You can prove it by algebraic manipulation, you can prove it by contradiction, you'll see that in the second year of A-Level Maths, but here we're going to particularly look at a type of proof called proof by induction. Now, proof by induction, it only has a limited set of theorems that it can work for. It can only work for theorems that involve whole positive numbers. Okay, so it can't work for fractions. You can't suddenly insert a fraction into this theorem that we're using of proof by induction to get a correct statement. It doesn't work for negative numbers either. You may have to adapt this type of proof slightly and you could get it to work, but generally it's only positive integers, positive whole numbers, that this type of proof is going to work for. So I'm going to give you a little bit of an analogy first, the way that I consider, the way that I think about proof by induction working, and hopefully it will help later on in the video how you see the proof starting to be constructed. Now the analogy that I'm going to use is that it's similar to building a wall. So here it's Donald Trump's favourite way of proving a statement. So consider this statement here. If you can prove that you can build the foundation layer of your wall, and then however high your wall is, so however high up it grows, you can always build the next layer. And the question to consider is, how high could your wall potentially be after continually building? And hopefully you've got to the point where you think, well, yeah, it could be infinitely high, because if we can build base layer 1, and we prove that we can build base layer 1, and we can prove that we can always build the next layer, we can build layer 2. And if we know we can build the next layer, we can build level 3. And if we know we can build the next layer, we can build level 4. And if we can build the next layer, we can build level 5, etc., etc., etc. Okay, so that's how it works, in that we're going to go through a few separate steps. The first step is to prove the case is true for n equals 1, the base level of our mathematical theorem. In the second step, we're going to assume that our theorem works for a certain k value. Now, our theorem is going to be in terms of n, but we assume that our theorem works all the way up to a k level. And then the next step is to prove that the next step up from that, the k plus 1 level of the theorem, works as well. Now, this is generally the hardest, most algebraic manipulation you'll have to do in this type of question here. The first two come out pretty quickly. The third step is the long algebraic step. And the fourth step here is the conclusion. So you need to wrap things up at the end and just summarize what you've done in the first three steps there. So the classical statement of proving something is you need to convince three people. You need to convince yourself in this proof, you need to convince your friend that this proof works, but you also need to convince your enemy that this proof works as well. So don't leave any gaps and jumps in logic when you're completing these types of proof. It must be watertight so that even your enemy can't find any holes in your proof or can't understand the steps that you've gone through. Okay. So we're going to look at two examples here. The first example of a statement that we're going to prove by induction is that the sum of 2r minus 1 is equal to n squared, where we add up all of the numbers, or substitute in all of the numbers from 1 up to n. Okay. Now, you will always generally see this type of symbol on a proof by induction statement. Now this symbol here is representing the fact that n here is a positive integer. So that means that we can't add up this set of numbers up to 7/3 or minus 63 or anything like that. It's always positive whole numbers, and these types of proof generally only work for positive whole numbers. And let's have a look at our theorem here. This is what we're going to be adding together. And this is a shortcut formula for what the summation of all of these things could equal. Okay. So the first thing we need to do is the base step. So what we're going to do is we're going to prove our theorem works for n equals 1. So on the left hand side, we're just going to substitute in n equals 1 on the top of this summation series. So we're going to be adding up the numbers from 1 to 1 substituted into this formula here. This is where we're substituting into. This is effectively the statements that we're adding up. So substitute 1 in and you get 2 times 1 minus your 1 and we get 1. Let's now look at the right hand side. Now the right hand side just asks for you to take the highest number in your sequence that you're substituting in and square it, and that's a shortcut way, a formula effectively, of finding the summation of these types of numbers. So you do 1 squared and you also get 1. So because the left hand side here is equal to the right hand side, we have proved our base step works. The statement has now been proven for the base step. We have effectively proven that we can build that foundation layer on our wall. The next step is the assumption step, so we're going to assume that our theorem works up to some k value. If we consider k as 1, then what we can do is in the next step we're going to assume, we're going to prove that our theorem also works for up to 2. So we're going to assume here that our theorem works up to a certain level, so substituting in all the numbers up to k, 1 plus 3 plus 5 plus 7 plus 9, all the way up to 2k minus 1. So just write out the first few terms in your sequence and the last one, and it will help give you a better picture of what's going to come next. And this is going to equal k squared. So effectively what you've done here is you've just written out your statement here, the statement you're trying to prove, but just substituting k where n appears. And maybe write out a few steps to just be able to visualize what the series summation is that you're adding up. So we can assume here that this theorem is allowed. We can assume that this is working, and this k squared is a shortcut for adding up these terms here. It does feel like a little bit of a cheat way of doing it the first time you see this, but soon you'll identify the inductive step as the important step. Now we're going to prove that from this theorem here, that adding up the numbers from 1 to k substituted into this formula works, or k plus 1 substituted into this formula works. So in this, we're going to be substituting in 1, 2, 3, 4, 5, 6, all the way up to k and k plus 1. So here is what the formula will look like substituting up to k, and then we also need the extra k plus 1 step as well. So substituting in k plus 1 will give you this expression at the end here. Now we can replace the majority of this with our assumption step. You can see here and here that we could effectively shortcut all of this summation here for just what k squared is. So effectively it's just k squared plus 2k plus 1. So you're going to simplify in these series type proofs a lot of your summation for just a small formula that you're given in your formula. Okay, that you're given in your theorem. Okay, and then you'll have to add on the n plus 1th step. So it's always going to be the case that this part here comes from your assumption, and it's always going to be the case that this part here comes from your k plus 1th term, when you substitute k plus 1 into the things you're adding up. Okay, and we can simplify this if we expand these brackets here and do a bit of factorising, we get k plus 1 squared. Now is that what we were looking for? Well, yeah, I suppose it is really, because if the series up to k allows us to use the formula of k squared, then the series with a top number of k plus 1 must be k plus 1 squared. So therefore we've finished the third step there. We've proven that if our theorem works for the series of 1 up to k, given this shortcut here, that our theorem from 1 up to k plus 1 also works in a very exact similar way as it did here. Great, so that's the inductive step done. And all you need to write for a conclusion is this, and it's the roughly the same layout each time. As we have shown our theorem true for n equals 1, and given that n equals k is true, we have also shown that n equals k plus 1 is true. Therefore, by mathematical induction, restate your theorem. It is true for all n existing in the integers, positive integers. Now make sure you don't forget this step at the end here. I've known people to lose a mark for not writing the fact that our theorem is only true for positive integers. We've not proven it for fractions, we've not proven it for decimal numbers, we've only proved it for whole amounts, positive whole amounts in our theorem. Okay. So that's the first one. We'll have a look at a second one now. So this is the series of r squared. We did say that in series 5 we'd come back and prove this. So let's go ahead and do that. So first step is the base step. Substitute n equals 1 in. So on the left hand side you're going to get the series from 1 up to 1 of r squared. So you're substituting 1 into r squared and you're getting 1. On the right hand side you're substituting in 1. And once you've computed all the n values of 1 and done all your maths there, you can simplify all of this to 1 as well. Now it's not always going to simplify to 1, just in this case here. In the previous example it simplified to 1 in both cases. But what you're looking for in this base step is for the left hand side to equal the right hand side. And as long as that happens, then you're good to go on your basis step. The next step is obviously the assumption step, so we're going to assume that our theorem works up to a certain value k, and that we can simplify this series with the formula of 1/6 k plus 1, 2k plus 1. I know it feels like cheating, I know it feels like, well, we can't just assume that. That's not this. The assumption bit is not the important step in these proof by induction questions. It's the next step where we prove that the next layer up works. Because in that step, if we've proven that n equals 1 works and we prove that the next step up works, then we prove that 2 works. And if we know that 2 works and we know the next step up works, then we know that 3 works, etc, etc, etc. It's the inductive part of this question here, or inductive part of your workings here, that are the important parts. So in the inductive step here, we want to prove this exact theorem works for k plus 1 as well. So substitute k plus 1 in, and it's going to be the same summation for the first k substitutions, but then remember we've got 1 extra, so it's plus k plus 1 squared. Okay, and what we will be able to do then is simplify the majority of the first part of this summation with our formula from the assumption step, and then add on the k plus 1 step. So it's always the case that it's going to be this assumption step here and the k plus 1th term here. Okay, so what we can do now is a little bit of clever factorizing. So what I would do is write each of these two statements as fractions over 6 and then try and combine, and then we can do some clever factorization as well. We've got k plus 1 in both the terms. We've got k and 2k plus 1 on the left and an extra 6k plus 1 on the right. Expand those brackets and simplify or factorize, and we get k plus 1, k plus 2, and 2k plus 3. Now, is that what we were expecting? Well, if we substitute k plus 1 in here, then that will give us k plus 1. If we substitute k plus 1 in here, we get k plus 2, and if we put in k plus 1 in here, we're going to get 2k plus 2 plus the extra 1, so we get 2k plus 3, which is exactly what we were looking for. Great. So now that we've proven the inductive step of this question here, we can now write our conclusion. As we have shown our theorem true for n equals 1, and given that n equals k is true, we have also proven true for n equals k plus 1. Therefore, by mathematical induction, write your series out for all positive integers. Okay. Right, one more, because this one is quite a difficult one and much more different to the ones we've seen in the series chapter. This is the series of your number times by 2 to the power of your number. So if it was substituting in 3, it'd be 3 times 2 to the power of 3. So that would be 3 times 8, which is 24. So you'd be adding up 24 when r equals 3. And quite a difficult summation formula this. 2 brackets, 1 plus n minus 1 bracket 2n. So much different to the series types of questions we've seen before, but it's proof by induction, so we're going to be following the same sort of steps. we prove that we can build the foundation of our wall. So substituting n equals 1 on the left-hand side, so substituting in 1 into this expression here, the things that we are summating, we get 2. And on the right-hand side, substitute in n equals 1, and we get 2 as well. Great, so left-hand side equals right-hand side, proven the base step. Okay, next step, the assumption step, so the cheating step effectively here. We're going to assume our statement is true for n equals k. So, a good idea would be to write out a few of the first terms up until the value n equals k. Really, there should be a k on the top here. And then this equals the formula with k substituted in. So it's 2 brackets, 1 plus k minus 1 brackets, 2k. Okay, and we're going to be using this in the third part of our question. So, the inductive step now. So this is the important step where we're trying to prove our theorem is true for k plus 1. What we could do is just think before we start what we want to show. So WTS, I sometimes write when it's a difficult proof, is what we want to show. And what we want to show is that the series for k plus 1, where r equals 1 of r 2 to the power of r, is going to equal this theorem here, but not with k's, with k plus 1's. So it's going to be 2 brackets, 1 plus... now if k here is k plus 1, then it would cancel out the 1 minus 1 there. So it's just going to be k, and then 2 to the power of k plus 1. So that's what I want to show. And sometimes it's useful to have that as a target for what you want to be doing in your inductive step. Oh, brilliant, I've got it here, perfect. Okay, so what I want to show is this. Now let's take the series for the first k terms, and then we want k plus 1th term to be there as well. So add on k plus 1 bracket 2k plus 1 as a power. So we can simplify a lot of this using our theorem. We can use this mathematical statement here. 2 brackets 1 plus k minus 1 bracket 2 to the power k. Plus the k plus 1th term, because that wasn't simplified in our assumption step. So we're proving the next level up here. Okay, so now to expand your brackets, so expanding the brackets from the first one and expanding the brackets from the second one, not that we really did that. Moving on, expand your brackets a little bit, so we can simplify this 2 and this 2 to the power of k to get 2 to the power of k plus 1. And now we've effectively got k plus k minus 1 and k plus 1 with factors of 2 to the power of k plus 1. So let's factor out that 2k plus 1. So now we've got 2 plus k minus 1 add k plus 1. And then simplifying that, we've got 2 plus 2k times 2k plus 1. And remember what we wanted to show? We wanted a 2 as a factor on the outside of a bracket, so refactorize that and we'll have 2 brackets k plus 1, so 1 plus k bracket 2 to the power of k plus 1. And that's exactly what we wanted to show. You can always go back and rewind the video a little bit, and this is what we were wanting to show. This is equal to our WTS. Okay. And then comes the conclusion. So as we have proven our theorem true for n equals 1, we have proven our theorem true for n equals k plus 1. Therefore, by mathematical induction, our theorem is true for positive integers. Alright then, so your turn to have a practice here. I'm going to go through this question straight after you've had a go. So pause the video and do spend a little bit of time having a go at this question here. Alright then, well done for having a go at this question here. I'm just going to divide up my page just so that I've got enough space to get this question started. So step 1 is to prove true for n equals 1. So my theorem is on the left hand side, I'm going to have a series from 1 up to 1 of r minus 1. So that's going to be 1 times 1 minus 1, which is going to be 0. So 0 is what I get on my left-hand side. On the right-hand side, substituting in 1, I'm going to get a third of 1 times 2 times 0. That's great. So that is 0 as well. So left-hand side equals right-hand side. We have proven our theorem true for n equals 1. Step 2. Assume our theorem is true for n equals k. So assume for n equals k is true. Okay, so our theorem, which is k, a series up to k of r minus 1. Now what would this be? Well, it would be 0 as the first term. We worked that out earlier. The second term, when I substitute in 2, is going to give you 2. Step 3 is going to give you 3 times 2, which is 6. Step 4 is going to be 4 times 3, which is 12. All the way up to k minus 1. And this theorem here is going to be true, and a shortcut way of writing this mathematical series summation here is going to be a third, but not n. We're going to write k instead, k plus 1, k minus 1. So I get a sense in this question here immediately I'm going to be doing a lot of factorising here, but that's okay. I'm okay at factorising. Step 3 here is now prove true for n equals k plus 1. Prove true for n equals k plus 1. So in this case here, what we want to show, I'll do a little WTS, I find that always quite useful, is equal to, is the series of r minus 1, which is going to be a third k plus 1. So what I'm doing now is I'm substituting k plus 1 in here, and in here. So I'm going to get k plus 2 as the second bracket, and just bog standard k as the third bracket there, because the plus 1 cancel out with a minus 1. So out of my WTS, I'll start on the left-hand side. The left-hand side is the series of 1 up to k plus 1 of r minus 1. So from this, I can write out the first few digits in my series. So 2 plus 6 plus 12 plus k brackets k minus 1. That's the kth step, but we also need the k plus 1th step. So it's going to be k plus 1 times k, just substituting k plus 1 into this part here. Now I can simplify a lot of this with my theorem in the assumption. I can assume that a lot of this, in fact all of this, will simplify to this. So I'm going to have a third k plus 1, k minus 1, and then plus the k plus 1th term. Now what I'll do to speed up the process here is I'll write this as a fraction over 3, just like I've got here. And now it's time to do some cheeky bit of factorising, some clever factorising, and what my target is the right-hand side of this WTS, the right-hand side of the want to show. So factor out your third and see what factors we've also got. We've also got a k, we've also got a k in both of these terms here, and a k plus 1, so quite a lot of the factorising has now been done here. In the left hand, we've got k minus 1, and in the right hand we've still got 3. So finally this is going to be a third k plus 1, k plus 2, which is exactly what we wanted on the right hand side of what we wanted to show. So perfect, we've proven the inductive step that we can build the next layer of our wall, or effectively that our theorem works for the value k plus 1 if we know that the value k works. And the fourth step is to write the conclusion. So given that n equals 1 is true, and given n equals k is true, we have shown or proven that that n equals k plus 1 is also true. So my pen's a little bit laggy here. Is also true. And then I'm just going to let you carry on here. Therefore, by mathematical induction, this theorem here is true for all n existing in real integers. Okay, so that's what we're looking for there in the conclusion. You can see a bunch of conclusions in the previous slides to this. Right, thanks very much for watching this video. Now you will need lots of practice on this exercise 8a. Make sure you do roughly all of the questions in the exercise 8a. They are really difficult questions, and when you see this for the first time, it is difficult, and it's difficult to get your head around it. What are the steps? What do I need to do when? So feel free to re-watch this video. Feel free to re-watch each of the individual 3 proofs that we went through and the 4th proof on this final one here, and take it step by step. Go slowly, ask your teacher for help if you need any, and persevere. Do persevere through these difficult questions here, but it will get easier the more you do, and the more you practice, and the more you build this skill. Okay, thanks very much for watching this video.